Hello, this is the 9th video in this series on random number generators, accompanying the book Random Number Generators, Principles and Practices, and the third in the series on entropy extractors. This video took a bit longer than expected because I've been very busy at work. We've got a number of test chips I've been designing, and so I didn't really have time to make these videos very quickly. But here we are, and we're going to cover single input extractors, correlation suppressors, and whiteners, or debiasers, and not necessarily in that order. So let's get on with it. A single input extractor, we know what an entropy source is. So an entropy extractor takes the data from that entropy source, which is partially entropic, it's not fully random, and squishes it down to try and make it more random, so you get less data out, but at a higher quality randomness, and hopefully full entropy, which is every bit being independent and unbiased. So what could you use as this function to convert that data? Well, we call it single input because, as the picture says, you input some data to that function, it outputs some data, and there's only one source of input, which is the entropy source. And a hash function is an example of an algorithm you might use. And this is a function, it's sometimes known as a one-way function. It's where the data you put in, you can put as much data as you like in, but you get out a fixed size string, and that can mirror what an entropy extractor does. And part of the goal of a hash function, a cryptographic hash function, is that it's impossible to work out what the input data is from the output data, or impossible to generate, having seen the output, to generate data which would give you that same output, or to generate two pieces of different data which would have the same output. And those are the primary cryptographic properties that you want from a hash function, but also that enables it to be used as an extractor, but imperfectly, and we'll get to that. So there's a proof called on the impossibility of private key cryptography with weakly random keys. And what they mean by that is when you have a one-time pad scheme where you XOR what's called a one-time pad, is the full entropy string of bits, with your data, and you send it along, and then the person at the other end has the same pad, and they XOR it to take off that encryption, and they get the plain text back. And here they're just talking about a single bit. This paper proves that if you've got a single weak source of entropy, and by weak they mean anything that's not full entropy, which of course doesn't exist, so any entropy source, you can't get enough entropy to perfectly encrypt that one bit of data that you send. There's another class called seeded extractors, which we're not covering this time round. And so an example here is cbcmac or cmac. MAC stands for message authentication code, because it's usually used to authenticate messages in communication protocols, but here it's being used to be an entropy extractor. And so you have a key, which is a fixed size string of full entropy bits, and you then input your data from the entropy source, and you output data. And this is a good construct in the sense that this works, and provided you have this full entropy key input, but it raises the question, why would you need an extractor to generate full entropy data when you have a source of full entropy data in the form of the key? So this is a little futile when you think about, well, this universe can't give us full entropy data, And so there's no way I can actually get to a full entropy string to use as the key to feed a mac function or any other keyed extractor, because the first extractor in the universe doesn't have any source of uniform data with which to produce more uniform data to use for the input to other extractors. So you can use this and get arbitrarily close, but not perfectly close. There's a proof by Evgeny Dodis and a few other people that cbcmac and hmac, which is another form of message authentication code, are good entropy extractors, but in a different way. They say you put in some data, an amount of data with an amount of entropy, and what you get out is close to uniform or computationally indistinguishable from uniform up to some limit. So there's some epsilon that says how far you are away from that perfect ideal. And so the output properties, the cryptographic properties of the output, are couched in terms of the computational difficulty of distinguishing it from random, rather than it being full entropy. So it turns it from a what we think of in cryptography as a semantically secure source of data. There's no algorithmic connectivity within that data that you could use to unwind it, versus a computationally secure, which says, yeah, you could break it if you had infinite amounts of computational power, but you don't, so you can't. And just to get a little bit of an idea of what goes on in the proof, this is now there's a lot that goes on in the proof, but here it says the first thing to note is that modeling the compression function of SHA-1, which is a hash function, for example, as a random function or as a family of random functions. So what they mean there is a function which, rather than just doing one thing, is randomized, and the randomizing element is the input key. But a hash function doesn't have an input key; it's a single input algorithm. It says, is a strict relaxation to modeling SHA-1 as a single unkeyed function, as a random function. And goes on to say, for example, in the cascade construction, which is the internal architecture of SHA-1, the probability of two L block inputs that differ only in their first block are mapped to the same k-bit output is L over 2k. While for a random function, this is probably 1 over 2k. So let's say, so you have a higher probability of collision of L relative to a randomized function, which would be something like a Mac with a randomized input on the key. And that's because only the last block, if they're all the same except for the last block, then only the width of that last block can count for avoiding the collision. So there are other things you could do. We'll look at those first because they're a lot simpler. Using source statistics, not just min entropy. So instead of just assuming the min entropy of the input data, we're going to assume we know more about it, in particular its statistics. So let's say we've got a 50% source of entropy. The entropy rate is 0.5. Or you're producing 100 bits, you get 50 bits of entropy in that data. So we could have some data with bias and serial correlation, and then we have a string here, which was generated with both bias and serial correlation. The bias was 0.72 and the correlation was negative 0.05 something. It could just be squished to one end. Now these two numbers here, in the bias and serial correlation, if you have data with that, you actually have 50% entropy. And I spent a bit of time working out how to a pair of numbers which gave us 50% entropy. Or you could have half the data being full entropy and the other half data being all zeros or no entropy. And you might know that, and you'd know the latter half was full entropy and the other half isn't. So you could think of a really simple extractor for this case of chop it in half and just take the second half, and then you get full entropy data. But this is assuming you know more about the input than just the min entropy. You know the min entropy is 0.5, but you don't know how the entropy is distributed among the bits. Here you do, and so it's very easy to extract it. You could have just biased data, and here the bias is 0.7071. Well, these digits go on, but that is equal to 50% min entropy. We could have data that's just correlated, and the correlation is root 2 minus 1. And so here we have this data that's serially correlated, and you see some 5s and some A's, things you might expect with negative serial correlation in this case. So let's first talk about decorrelation. We'll look at the case where we know we've got serial correlation in the source data, and we want to reduce it. And here's an example of data that is serially correlated, and this is a parallelogram. So what this is showing is the serial correlation between a bit and a bit that is one bit away from it in the data pattern, or 2 bits away from it in the data pattern, or 3, and so on. So when you're comparing bits that are different distances away on the within the data, you're showing what the correlation change is as that distance increases. And here this graph goes up to 15, a gap of 15 bits between the pair of bits we're comparing throughout the data. So obviously the 0th place on the x-axis is comparing the bit with itself, so you have 100% correlation. And the red line is the serial correlation, and the green line is for that serial correlation, assuming no bias, the probability that a bit xi is the same as the next bit, or the bit xi plus n, which is the number on the x-axis, is giving that probability that those bits are the same. And this is for positively correlated data. If it was negative, it would be hopping up and down. So this is a nicer graph to show this with positive serial correlation. And you can see that that probability is about 0.85. And then this turns down to about 0.74, I think, and it keeps going down and asymptotically approaches 0.5, which is, you know, uncorrelated, because the probability that a bit is the same as the bit it's compared against is 0.5. So the serial correlation goes down to 0, and the probability of bits being the same at the gap we're looking at is gets to 0.5 as you increase the separation between the bits. Because obviously, if you are this correlated, 0.7, the serial correlation of this data is 0.7, between adjacent bits, then your serial correlation with a bit 2 bits away is weaker, because this bit is partially correlated to this bit, and this is partially correlated to this, and so the correlation gets weaker and weaker and weaker until it's close to there being none. Now, this never reaches 0; it gets asymptotically close. Now, why might we be interested in that? Well, we looked at the use of XOR as a very simple 2-input extractor. And if we were XORing pairwise bits in serially correlated data, we'd get a bad result, because their propensity to be the same would lead to a propensity to get a 0 out of the XOR, and so you'd get biased data. Or if they had a propensity to be different, then you'd get ones out of the XOR more often than not, and so again you'd get biased data the other way. But here it says, well, if we space the bits out we're XORing together, there's going to be less correlation, therefore the XOR is going to work better as an extractor. So here's a circuit we can build which takes advantage of that. So the data you have, the serial bitwise data you have, goes into the A input of the XOR. And if you're not familiar with digital logic, these boxes here each are flip-flops, and so their little triangle represents the clock input, and there's a clock feeding all of them, the same clock. And when the clock fires, the data on the input gets passed to the data on the output. So it acts like a delay line or a shift line, where the data coming in each clock period gets shifted from here to here to here. So this delay line is filling up with bits that are coming in through the exclusive OR. The data is coming out the other end and being fed in here. And so then if you feed more than 7 bits of data in, you start XORing it, what's coming out of the end of this delay line with what's in the input. And so the bit that this sees is 7 bits away in the input pattern from the current bit that's being input. So there's this gap of 7 between them. And if in our input data we couldn't see correlation up to 7 bits, that would work just fine. In the sense that the bits were almost completely uncorrelated, and so the XOR would work well. And then you would feed in an amount of data. Say you would feed in 16 bits into this, and it would circulate around, accumulating entropy in these bits. And then we would take out 4 bits. So every 16 bits in, we'd take out 4 bits, and those 4 bits would be higher entropy. And this is on the assumption that there's serial correlation and not something going on which is going to undermine our basic assumption. Now, if you count these delay line elements, you'll see there's 7 of them, and 7 is a prime number. And that's not a mistake. There's a reason for that. In the Intel random number generator, we have one of these circuits well, one of the things it does is slow down the rate of the entropy source by a factor of 4, because that's what we do. We feed in 16 bits and we take out 4. The length being prime. Imagine this was not prime. Imagine this was 8 bits, and we were feeding in 8 bits at a time and taking out 4. So you'd have 8 bits, and they'd land in these areas, and there's 1 bit that would land here, and then 8 bits later it would rotate around and get XOR'd, and the result of the XORing of that bit would land back here, and it would happen again. It would keep landing here, so you'd get the data here accumulating entropy from those bits, but never landing on a spot which is being used for the output, so that data would never get used. By making sure the amount of data you're inputting every time for each time you pull some data out is relatively prime to the length of the chain, you know that those bits are going to rotate around and sooner or later land on the region that's being pulled out. So all the data, all the entropy gets used, not just some of it. So in the Intel chips, it's 11 long, and that's because from the entropy source, we can't detect correlation 11 bits out. There's some negative correlation due to the feedback, and that diminishes as the gap increases, and 11 is good enough. You could make it longer if your correlation was longer. You need to look at your data to see. So this is a very simple circuit, and quite effective at increasing the entropy when you have a correlated source of data. And it doesn't matter if it's biased as well. It's dealing with the correlation, and the XOR is improving the bias, because we're taking bit pairs that are not correlated. There's an algorithm which has a history of being used as an extractor, but it's not an extractor. It's a debiaser, and it's called the von Neumann D. I call it the von Neumann debiaser. It's more commonly called the von Neumann whitener, which comes from the idea of the spectral content of the data being white, or if you did a Fourier transform over the data to look at the frequency components, you'd see that it was uniform across the spectrum. But that's what full entropy random data should look like. But really what it's doing is debiasing. So it's taking biased data and turning it into unbiased data. So here we have a source of data. It's bias. This isn't actually bias of 0.3. It came from source which had a bias of 0.3. So I just stuck it into my program that generates bias data and said, give me data with a bias of 0.3, and took out a bit string that came out of it of 32 bits. And obviously you can't get bias of 0.3 because 0.3 times 32 is not a whole number. But so we go through the algorithm and we split it into bit pairs. So just this, and we've put a gap between each of the bit pairs so we can see them clearly. And then we say if we have a 0, 0, don't output anything. If we have a 1, 1, don't output anything. If we have a 0, 1, output a 0. And if we have a 1, 0, output a 1. And so we look through here and we've got 0, so nothing, 0 through nothing. 1, 0, so we get a 1. 0, 1, we get a 0. 0, 1, we get a 0. Then nothing. 1, 0, 0, 1. And so the bit string we get out is 1, 0, 0, 1, 0, 0, 1. And this has a bias of 3/7 because there's 7 bits of data and 3 of them are set. But that's as close to uniform as you can actually get with this because we have 7 bits of data. If we can't have, if it was 4/7, it would be equally minimally biased as 3/7. There isn't an integer half of 7, right? So, and this should tell us a few things. With the von Neumann debiaser, the amount of data you get out is not guaranteed. We got 7 bits out because there were 7 bit pairs which happened to be neither 0, 0 or 1, 1, but that can vary from sample to sample. So it doesn't give you a deterministic amount of data out. And the other important note is this doesn't work for serially correlated data. If the data was serially correlated, then you'd see a higher proportion of 1 zeros, or say it was negatively serially correlated, you'd see a higher proportion of 1 zeros and 0 1s than we would zeros or 0 zeros or 1 1s. And if you were positively serially correlated, you'd see more 0 zeros and 1 1s, and depending on the bias, you'd get more of one than the other. And you'd end up with a biased output. So serial correlation ends up turning into bias of the output of this algorithm. And that's not what you want. The point of this is it takes biased data and turns it into less biased data. And this is a mistake that's often made. People will stick a von Neumann debiaser in front of an entropy source which has serial correlation, and then it doesn't work as well as it should. There is a variation on this called the evalperez debiaser. And this is a derivation of the von Neumann. So we notice that when we have the von Neumann debiaser, we're throwing away a lot of data. For each of the bit pairs that we use, we only use 1 bit, and then there's about half the bit pairs we don't use. The von Neumann debiaser takes all that data which we've thrown away and uses it again iteratively. So it generates a string from the output of the von Neumann debiaser plus the stuff that was thrown away, and generates a new string and then does it again, and it iterates a few times until some limit is reached. And again, this doesn't work for serially correlated data for the same reason, but it's quite a bit more efficient. So here's the definition in the paper by evalperez, and of course it's written in mathematical gobbledygook, so it took me a little while to read this and untangle what was being said. But here's what's going on in a clearer form. So we've got our bit string, the same as we had before, and our bias is 9 out of 32, which is what we happen to get from a 0.3 biased source. You run this data through the von Neumann debiaser, and we get this string that we got out before, and that becomes the first string of the output. And then each of the bit pairs, we take them pair by pair and exclusive all the 2 bits together and get 1 bit. So 0 0 gives us a 0, another 0, a 1 0 gives us a 1, and that's what we're seeing here: 0 0 1 and so on. And you can go through the data and convince yourself that this is the XOR of the bit pairs within that source string. Then the final part is made from looking at the bit pairs and saying, if they are a 0, 0, put in a 0. If they are a 1, 1, and that's this 1, 1 here, you get a 1. So those are values that we were otherwise throwing away. And that becomes the third part. So we produce another output string, and we see here the bias is now 11 out of 32, not 9 out of 32, which is better. And I say here, repeat until done. So we would iterate this. We would take this data, pass it into the evalperez debiaser, and get another output and repeat it a few times. So one of the questions there is how many times? So here is the input to output data size of the evalperez debiaser. And on the x-axis is the bias of the data. So 1 is all 1s, 0 is all 0s, 0.5 is full entropy input with a bias of a half, and then everything else on the x-axis is positively or negatively biased data. And what we see is the amount of data you get out of this algorithm if you have all zeros, all ones, is nothing. The y-axis is the amount of data, or the ratio of the data out to the data in we got. But this 1, 2, 3, 4, 5 is the number of iterations of the algorithm. So we have this algorithm, we're iterating it 1 times and 2 times and 3 times and so on, up to 5 times. And feeding in a megabyte of data at various different biases and seeing how much data we get out. And we see that with one iteration, we get some data out, and we get about 20% of the data out for perfect input data, and less as you get less perfect. But if you iterate twice, you get quite a lot more data out. You're up to 0.4. 3 times you're up to 0.5.5-ish, and so on, and it goes up. So the size of the output data varies with the bias of the input data, and it increases with the number of iterations of the algorithm you run over that data. So this gives us a hazard. So here we ran some data through the evalperez debiaser using an iteration limits from 1 to 6, and the input size was a megabyte of data, or a MIBI-byte to be accurate. So 8,388,606 bits, or 1,048,576 bytes. The input bias was set to 0.35, and that implies an entropy rate of 0.06125, so a 61.25% entropy rate. So if we multiply that by that, we find that we have 651,677 bytes of full entropy in that data. So we run it through the debiaser, and we get a file size of 238,000 bytes. So the input to output ratio, this divided by this, gives us 0.227. And as we do more iterations, we get more data out. But we find for these last cases, 4, 5, and 6, we're getting more data out than the amount of entropy. So 651,677, this is 658,612, and it goes up from there. So this is violating the rules of entropy extractors. We're getting more data out than we have input entropy in, so we cannot be having full entropy in this output data. And when you think about that, this is a fixed algorithm. You're putting in some data, and it's got some amount of entropy, so there's a number of different possible values. and that is only, so let's say that there were 1,000 bits, but only 2 to the 500 different values. So because it's not full entropy, we would have only 2 to the 500 output patterns coming out, but there would be more than 2 to the 500 patterns coming out because we've got a larger amount of data coming out than we're putting in, or a larger amount of data coming out than entropy we're putting in. And so you'd find duplicates of values coming out more often than you should. So now we're looking at single input extractors that of the sort we commonly use that only make a min entropy assumption about the input. And here we're going to look at one of the extractors from SP 800-90B. And this is the standard that NIST provides for entropy extractors and entropy sources. In that spec, it calls them conditioners, not extractors. The academic term is extractor. I don't know why NIST chose to use a different term. But it says this, which I copied from the spec: 3 unkeyed functions have been vetted for an unkeyed conditioning component. So what they mean by unkeyed is a single input algorithm. There's no key input. And the first line is any approved hash function specified in FIPS 180 or FIPS 202. So that would be SHA-1, SHA-2, SHA-3, and so on. Then there's 2 others, the hash derivation functions specified in 90A, which we're not going to look at here because we're going to look at that when we look at PRNGs, which is covered by 90A, or the block cipher derivation function, which for the same reason we're not going to look at here. So we'll look at this first case, and what we have is exactly the diagram we had early on in this video of we have an entropy source, we have a hash function, and hopefully we get full entropy out, and it's a single input algorithm. So do we get full entropy out? Well, SP 800-90B gives us some equations to determine how much entropy we get out. So it says the entropy out, H out, is equal to this function output entropy, and is a function of the number of bits of data in, the number of bits of data out, the internal width of the cryptographic function we're using, and the entropy in. So the entropy rate is the entropy in divided by the number of bits in. So you can think of these 2 numbers as defining the entropy rate of the source. And then it defines this function as being this lovely list of equations that you can plug those into a program and see what happens. So here L is it actually comes from the word length, but it's the number of blocks of data we're putting into the extractor. And here we're using SHA-256, which is one of the hash functions which is permitted in that spec. And so you can think of this as the extractor ratio. We're putting 2 blocks of data in for 1 block of data out, and that gives us the blue line. The x-axis is the entropy rate of that data that we're putting in. So say 20%, it's saying the entropy out is going to be somewhere like 50 bits of data out of 256 bits of data. And we see here it doesn't even, with L equals 2, so a 2-to-1 extractor ratio, it never even reaches 100%. So you need an extraction ratio which is greater than 2 to get to close to full entropy output. But with L equals 3, so 3 blocks of data in, 1 block of data out, we can follow the orange line, and we see that we approach the 256 line here because we're getting 256 bits of data out, and the entropy is 256. And so it gets up to here, it saturates close to 256, and there we go. Now, what this is really telling you is if I have a source which is, say, 0.3, and I go up here and I can say what extractor ratio do I need to extract full entropy data from that? And you might look at this and say, well, the next the next lowest corner on this curve is L equals 6. So I could use a 6-to-1 extractor ratio. But maybe you're worried about your entropy moving around a bit over time, so you might choose L equals 7 to give you some more margin. So you got this engineering choice of what extraction ratio do I use, and the higher the extraction ratio, the lower the entropy you can tolerate on the input. However, this is not completely clear cut, because although it looks like this saturates at 256, it never actually gets to 256. It's just an asymptotic approach. It's a very tight approach, but it never completely gets there. So, and this is in the spec, and they don't tell you how close to 100% entropy rate do you have to get to claim full entropy. It just says you can determine the entropy out using these equations, and then gives you equations that never give you full entropy. They just get very close. So what I did in the random number generators we use in Intel chips was I decided arbitrarily on 10 to the minus 2048 as being the limit, and then I ran along this curve until the delta between full entropy and the actual entropy we have is less than 1 in 10 to the minus 2048, which is over engineering it quite a lot. We could have a bigger gap than that. That's an astronomically small gap, and then show that the extraction ratio we're using, which is 4 here. So when you have that smaller gap, you end up traveling a little bit along the line, and we end up here from the green line's curve to where our gap between full entropy and what we have is that small. And you can see that with a 4-to-1 extraction ratio, we can tolerate about a 50% input entropy. But in fact, our entropy source is up this end between 0.8 and 1.0, usually 0.9 to 1.0. And so that's lots of margin between here and here. So that's they're nice curves from the point of view of it gives you a quite clear cutoff point for where you're very close to full entropy, but the specifications falls short of telling you how close you need to be to claim full entropy, and that's one of the errors in the spec. Now, SHA-256, the example, that has an internal width of 256, the width of the data path. The output size is 256, and the input size is therefore, with a 2-to-1 ratio, is 512 bits, with 4-to-1 is 1024, and so on. And so that's all we're doing in this talk. We've looked at how we can take advantage of things we know about the source that other than the min entropy, like serial correlation and bias, and then have very simple circuits to take advantage of that to improve the entropy quality of the data. And then we looked at cryptographic single input extractors, or just one of them. They're all pretty much the same. They're a bunch of crypto happening, but they're working on one input and they're mapping it to an output that looks more random. So I'll see you in the next one, where we'll look in greater detail at multiple input extractors, so keyed extractors and true multiple input extractors. So I'll see you in the next video. Thank you, and don't be afraid to ask questions below. I'm not getting many questions in the chat below, but I will answer them if you choose to do so. So thank you and goodbye.